We're about to spend quite a lot of time talking about tweaks to be made, various behaviors, and how we measure, record, and understand the memory usage with MongoDB. So it's worth taking a little step back and actually talking about how the MongoDB memory model functions. The first thing I'll mention is that we actually have a pretty decent summary of this in our reference documentation, which you can find here at this URL under storage. Several of the frequently asked questions and pieces that I'm about to cover are also covered on this page. So feel free to read through that as well if you wish. So the first thing to mention is that MongoDB uses memory mapped files. The memory map files are essentially implemented using the mmap system call. And what that means is when you call mmap on a series of files, in this case the MongoDB data files, those files are not entirely read into RAM. They don't actually touch physical memory at all. So if you imagine that your finite resources physical memory here, this is usually on the order of gigabytes, that we're starting to get into the terabyte range. You can imagine having, say, 64 gigabytes of memory. You can easily have 500 gigabytes of data. So how, when you call mmap on this and map all this data into memory, is it going to fit into 64? And the answer is it doesn't, right? So what actually happens is something called virtual memory is used instead. And without getting into a full description of how the virtual memory subsystem works, you can think of it like this. The files are all mapped into an addressable space in virtual memory and then are lazily loaded as MongoDB or any other process for that matter actually requests them. So you can imagine you create this virtual memory space, which let's say is 500, but essentially it extends on forever. There is a limit imposed by the operating system, but let's just pretend that it goes on forever. And this section here represents the the 500 gigs of data that you've then mapped in. These haven't actually been read off disk. They're not actually being loaded into physical memory until MongoDB says I actually need to access this particular document at this particular address. So you've got the MongoDB process out here, and it says I would like to access the data at that address space, please. That piece of data will then actually be loaded off disk. So if you imagine this is all a map to locations on disk. So it requests that particular piece of data. That then gets fetched off of the disk and loaded from there into the physical memory we mentioned earlier. That's what's going to count towards your resident memory and various other statistics that we've been looking at in MMS. So to summarize that a little bit, they're mapped into virtual memory. They're accessed lazily as needed, and at that point, when they are actually accessed, then they are read into physical memory. And essentially, that's the basic mechanism, because it gives MongoDB a very easy and simple way to access the data that it wants from disk without getting into a lot of writing its own memory management, things like this. So it just tells the kernel that it wants that particular piece of information that gets loaded into physical memory. So that's how things will basically continue until, of course, physical memory becomes full. So you've been lazily loading these pieces of data, these pages, into memory as you needed them. And eventually, with your 500 gigs of data, or however much it actually might be, you do finally fill up your physical memory. So with physical memory full, instead of just loading things in as needed, the kernel then actually has to find room for the next page that you ask for. So in other words, it has to find a page to discard, write that out to disk, get it out of memory, and then allocate the memory to the new data. So that's where the change sort of comes in. Previously, as we were just filling things up, it would just keep allocating more new and didn't have to worry about finding a page to get rid of. So now as you add a new page in, you've got to find one to get to page out as well. So how does the kernel actually make that decision? The kernel will decide which pages to discard based on, by default anyway, a very basic, simple algorithm. That algorithm is referred to as LRU. LRU stands for least recently used, which is exactly what it sounds like. The difference between this and, say, for example, a first in, first out type of algorithm would be that even if a piece of data, this is again physical memory, let's just imagine we've got a piece of data here. And it's actually the first piece of data that's been allocated in physical memory. It's first page, say, that MongoDB is actually requested. Now you might think that that's the obvious one when we get up to the fact that this has then filled up in a first in, first out. This would be the piece of data that's gotten rid of for the new piece of data that needs to be added in. However, least recently used, if this first piece of data has been continuously accessed, imagine it was, instead of being just a random piece of data, imagine it's actually a piece of an index here. And the index is constantly getting hit and getting scanned and various other things, and so this is actually has been quite recently used, as opposed to it is the first one in, but it has been recently used, and so it's not the one that's discarded. Instead, what we end up with is, say, a relatively cold page here, one that was paged in somewhere in the middle, halfway through the load into physical memory-ish, but has not been touched since, and as a result this is then the least recently used page. This is what is then discarded, and our new page can be allocated in physical memory.